Good morning. Thank you very much for the kind presentation and for the opportunity to be here today to share with you our experience in NGS in liquid biopsy samples. Briefly, and as it has been pointed out, as responsible for the molecular diagnostics in the pathology department, we have been experiencing this need to have more information, more gene sequence, more details from each sample, which at the same time are smaller samples. And this has moved, or made the movement from gene to these NGS approaches. On the other side, what we have been experiencing is that they are not the other samples, we have no sample, or patients are progressing, and therefore we need either to rebiopsy or to have another approach. And that's when liquid biopsies have taken their place, and we've started working with that. Initially, all these studies were performed with techniques as sensitive as possible, mostly digital PCR-based techniques, which worked pretty well. But of course, as we wanted more, we needed to switch somehow. And this is the evolution we have been experiencing at our center, and I think in many other centers it's now also a reality. We have been implementing during time these NGS approaches. At the same time, we started, at least in our hospital, working with liquid biopsy several years ago, initially in a gene by gene, or better to say, in a mutation by mutation basis, using digital PCR, and dreaming of having the possibility to use NGS to have a broad profiling of the molecular markers. And that was possible with the modification of the NGS approaches using the molecular barcoding that allowed to very accurately identify variants, and therefore achieving the sensitivity, not the same one as digital PCR, but at least something better than conventional PCR, conventional NGS, and getting down to about a 0.1% variant identification. Oops, sorry. So I will now don't go into many more detail of technical issues, which I'm sure the thermo people will very much better than me even explain to you. Tell you my experience with colorectal samples first, and afterwards with lung cancer. So with colorectal cancer, we have been using the Oncomine colon cfDNA assay that includes 14 genes, not whole genes, but the most frequent hotspots. Those genes involved in resistance, especially to therapies, but also the genes that are involved in pathogenesis of the tumor, and as I will show you later, are very, very useful to track the tumor during time. The workflow is very simple. It's DNA isolation, library preparation, template preparation, which at least in our center is automatized with a chef, sequencing, and finally analysis. And what we did was select a cohort of patients that had progressed to anti-EGFR therapy, mainly panitumumab, and analyze the samples at the time of progression. And you can see here the results. What we saw was a broad profile of mutations, coexistence of different mutations in different genes, which I think it's a proof of concept of the importance of using this wide gene-based analysis and not a one-by-one gene, especially at the time of progression, when we will be needing to decide next lines of therapy. That on the one side. On the other side, one thing very interesting for me here in these panels is that, as I told you, we are including genes such as APC, P53, or beta-catenin that are going to allow us to say, okay, here in this sample, I am capable of detecting tumoral DNA. Take, for example, patient 15 down here. The only thing we can see is a P53 mutation. We don't see any other mechanisms of resistance, KRAS, NRAS, BRAF whatsoever, but at least we can say, okay, here I have tumoral DNA. Have a look at patient 14. We see nothing, nothing at all. Okay, what's my interpretation of this? In this sample, I don't have enough tumoral DNA, at least to detect something. And with this, the consequences will be other. I cannot say we have no mechanisms of resistance, just that I can see them. One of the things we also did was try and rescue the samples before receiving the therapy. And as you can see here, most of the mutations were not present, so they had really developed during the treatment of the individual and therefore were mutants of persistence, so we could then decide the next therapy to give. Moving into lung cancer samples, our experience was similar. We started with a digital PCR for many years, and here it's a very representative case of an EGFR mutated patient in which we can detect the mutation at the very beginning, the sensitivity mutation, receives therapy with tyrosine kinase inhibitors, mutation goes down, after a certain time patient progresses, and we detect the mutation again in blue, and we can detect another mutation, the resistance mutation. So very nice, but of course, each time point, each sample had to be independently analyzed with the different targets we were looking for. When we had the opportunity to go to NGS, we tested some of these samples again, and you can see the results in the tables below. The results were very equivalent to what we had seen with digital PCR, but in addition, we saw this P53 mutation, so some more information there. With this, we analyzed a group of patients at the time of progression. In total, we had 22 cases. We were able to analyze 13. This is something to have in mind. In my view, NGS is fantastic. When we have enough sample, it's perfect to go for NGS and have a comprehensive picture of the mutational profile present there, but sometimes the quantity of DNA we can get from these plasma samples is limited. So in those cases, and that was the case here in these 9 cases that failed, we didn't have enough DNA to be capable of performing NGS. But in those that we did, we were able to detect the resistance mutation in almost more than half of the patients, either the T790 mutation alone or coexisting with P53 or with other mutations, and only in one case we didn't detect any additional mechanism of resistance. This was the lung, Oncomine lung cfDNA analyzing only mutations. We now have had the opportunity to test a next step in this type of NGS approaches, that is analyzing total nucleic acid. That means not only mutations, but also copy number variations and fusions. And I have to say that I am really happy with these results. Here you have represented the 20 cases without any selection that just arrived, or for which the oncologist had some special need and wanted to look something more. In some cases, 8 of them, we didn't detect anything. But in 4 of these cases, we were able to detect the EGFR mutations, 2 patients KRAS, and in 2 cases, we were able to detect gene fusions. And I will share with you one of these cases where we detected the gene fusion, because really, I have to say that it was a totally unexpected result. It was a sample from a lady that had been diagnosed several months before with lung adenocarcinoma. We had the tissue, we perform conventional biomarker testing, EGFR, ALK, ROS1, PD-L1 expression, no PD-L1 expression, no biomarker, so no targeted therapy, and the patient just received standard chemotherapy. After some months, she progressed, and that time is when we were testing these total nucleic acid assays, and we just tried to see if we were able to detect some copy number variation, something that could open a new line of therapy. So we went for this liquid biopsy screening, applied these tests, and we detected a RET fusion. As you know, RET fusion is one of these driver genes, normally uncommon, but that has options to targeted therapy. Of course, it was totally unexpected, so the first thing was, okay, let's try to confirm it with the tissue we have still available. So we performed FISH analysis, and we confirmed the RET fusion. We performed Oncomine also, and confirmed the RET fusion, and so the patient had the option to go for targeted therapy. And this is another case, different situation, a patient with EGFR mutated adenocarcinoma, treated with TKIs for some months, at some point starts progressing, and at least now in our center, what we are doing when the oncologists start to see patient progressing is try and look for resistance biomarkers in liquid biopsy. And we did so with real-time PCR arms at that time. We were able to detect the exon 19 deletion. Okay, we have tumoral DNA, great, but we didn't find the T790M. So what we did was go for this broader analysis and see if there were other mechanisms present. And I don't know if you can see it very clearly, but what we saw was that really the deletion was there, but also the T790M was detectable. Just in case there was some contamination or so on, what we did was independent extraction, independent cfDNA isolation, digital PCR, confirmation of this mutation, and proposed switching to third-line therapy. So, final things that we have to have in mind when analyzing liquid biopsies: tumoral DNA is maybe very diluted in normal DNA. The amount may be limited of cfDNA in the sample. The DNA is very fragmented, and of course, every time we want more and more information. So one thing that I highly recommend to those of you who start working with liquid biopsy is to optimize the pre-analytical phase. We are very used to optimize pre-analytical phases already, but here with liquid biopsy, it's also very important to adequate the size of the sample we are requesting. Until now, with 1, 2 ETA tubes, it was enough. But if we want to go for NGS, we need more DNA to have a correct sensitivity. So increase the number of tubes. Normally, it's possible, and it gives better results. Ensure the high quality of the DNA you're isolating. As I said, tumoral DNA may be diluted by genomic DNA from leukocytes, so it's important to ensure that we have this 180 base pair size. If we have higher size of our DNA, we may be losing some mutations, so check DNA quality. And finally, participate in the external quality controls and validation of the technology to be sure of what results we're giving. And also, one recommendation, I think, at least for me, for our oncologists, it's of great value, is to discuss the molecular results in multidisciplinary teams. We now have a molecular tumor board where we not only show the results, but also decide which testing we are performing at each time altogether. And I think it's of great benefit to all, especially to the ones who need at the end the results that the patients with the tumor. And this is our current practice, and now we are performing NGS at the very beginning in tissue always, unless we don't have enough material, and also liquid biopsy. We normally also collect liquid biopsies during follow-up, but more for research purposes. And when there's some evidence of progression, we take liquid biopsy again and try to perform analysis, mainly NGS, in those samples. If we got a negative result, then it's when in the molecular board we will decide whether we take another liquid biopsy or, if possible, we rebiopsy the patient. And with this, my take-home messages are that, in my opinion, ctDNA now it's a complementary strategy for the molecular analysis that allows, on the one side, a non-invasive analysis of tumor heterogeneity and also a dynamic biomarker monitoring. That it may provide a broad molecular analysis, including not only mutations, but also copy number variations, and as I showed you, gene fusions. That we need this comprehensive analysis if we want to do a real-time precision medicine, but that we have to standardize and validate our technology, and when possible, try to set up molecular tumor boards to discuss and take decisions. And my final slide, of course, is to acknowledge all the people in my team and also the oncologists with whom we are very tightly collaborating, and also Chris, Francesco, and Rosella from Thermo Fisher, who have been constantly supporting us. Thank you.